Have you ever dreamed of going back in time to meet your heroes, or jumping forward to see what the future holds? From Back to the Future to Doctor Who, the idea of time travel has captivated our imaginations for generations. But is it just a fantasy, or could it be a scientific reality? Today, we're diving deep into the mind-bending physics behind time travel. Stick around, because what we uncover might just change the way you see time itself. Let's start with a name you all know, Albert Einstein. His theories of relativity are the foundation for almost all modern discussions about time travel. Before Einstein, we thought of time as a universal constant, ticking away at the same rate for everyone, everywhere. But Einstein turned this idea on its head. He showed us that time is not absolute, it's relative. It can stretch and shrink depending on your speed and the strength of gravity around you. This phenomenon is called time dilation. First, let's talk about special relativity, which deals with speed. Einstein's theory says that the faster you move through space, the slower you move through time relative to a stationary observer. This isn't just a theory, it's been proven. We've sent atomic clocks on high-speed jets and into orbit on satellites. When they returned to Earth, they were ever so slightly behind the clocks that stayed on the ground. The difference is minuscule, just nanoseconds, but it's real. So, could you use this to travel to the future? Absolutely. Imagine you board a spaceship that can travel at, say, 99.9% the speed of light. You fly around for what feels like 5 years to you. When you return to Earth, you'd find that decades, maybe even centuries, have passed. You haven't aged much, but everyone you knew is long gone. You would have effectively leaped into the future. The challenge, of course, is building a spaceship that can reach such incredible speeds. The energy required would be astronomical, far beyond anything our current technology can achieve. But from a physics standpoint, traveling to the future is not only possible, it's an observed fact of our universe. Now, what about traveling to the past? This is where things get much, much trickier, and we need to bring in Einstein's other theory, general relativity. General relativity describes how massive objects, like planets and stars, warp the fabric of spacetime. Think of spacetime as a giant, stretchy sheet of rubber. If you place a heavy bowling ball in the middle, it creates a dip or a curve. That's essentially what gravity is, a curvature in spacetime. This curvature doesn't just affect space. It affects time too. This is known as gravitational time dilation. The stronger the gravity, the slower time passes. This has also been proven. Clocks on GPS satellites, which are in a weaker gravitational field than we are on Earth's surface, actually run slightly faster. We have to constantly adjust them to keep GPS systems accurate. If you were to hang out near a supermassive black hole where gravity is incredibly intense, time would slow down dramatically for you compared to someone on Earth. As we saw in the movie Interstellar, a few hours near the black hole Gargantua equated to decades back on Earth. Like with high speeds, strong gravity is another proven ticket to the future. But how does this help us go to the past? General relativity's equations allow for some very strange possibilities, one of which is the concept of closed timelike curves. These are essentially loops in spacetime that would allow you to travel along a path and end up back where when you started. The theoretical structures that might permit such paths are called wormholes. A wormhole, also known as an Einstein-Rosen bridge, is a hypothetical shortcut through spacetime. Imagine our rubber sheet again. Instead of traveling all the way across the surface from point A to point B, what if you could poke a hole through the sheet and connect them directly? That's a wormhole. It connects two different points in space and potentially two different points in time. If you could create a stable wormhole, you could theoretically take one mouth of the wormhole and accelerate it to near the speed of light, then bring it back. Due to time dilation, the moving mouth would have aged less than the stationary one. Now, if you entered the stationary mouth, you could potentially exit the moving mouth, not just at a different location, but at an earlier time. you would have traveled to the past. However, the if is a very big one. First, we have no evidence that wormholes actually exist. Second, even if they do, our current understanding suggests they would be incredibly unstable and collapse the instant anything tried to pass through them. To keep a wormhole open, you'd need something called exotic matter, a mysterious substance with negative mass or negative energy density. This kind of matter has never been observed and might not even be possible. So, while wormholes are a fascinating theoretical solution for a time machine, they remain firmly in the realm of science fiction for now. But let's say we overcome all these hurdles. We build our time machine, step inside, and set the dial for the past. This opens up a whole new can of worms, the paradoxes. The most famous is the grandfather paradox. What if you go back in time and prevent your grandparents from ever meeting? If they never meet, you're never born. But if you're never born, you couldn't have gone back in time to stop them in the first place. It's a logical contradiction that seems to make travel to the past impossible. Physicists have proposed a few ways to resolve this. One idea is the Novikov's self-consistency principle, which essentially states that the laws of physics forbid any action that would create a paradox. In this view, you can travel to the past, but you are not free to change it. Anything you do was already part of history. If you went back to save someone, you'd find that you were the mysterious stranger who saved them all along. Your actions would fulfill history, not alter it. Another fascinating possibility comes from the world of quantum mechanics, the many worlds interpretation. This theory suggests that every time a quantum measurement is made, a universe splits into multiple parallel universes, one for each possible outcome. If you travel to the past and change something, you don't actually change your own history. Instead, you create a new timeline, a new parallel universe. You could prevent your grandparents from meeting in that new universe, but it wouldn't erase you because you're from the original timeline where they did meet. This neatly solves the paradox, but at the cost of creating an infinite number of parallel realities. So, where does that leave us? Traveling to the future is a confirmed physical reality, limited only by our engineering capabilities. Hopping on a super-fast spaceship or hanging out near a black hole would absolutely work. Traveling to the past, however, is a different story. It's theoretically possible within the framework of general relativity, but it would require exotic matter we don't have and would raise profound questions about paradoxes and the nature of causality. Whether through self-consistency, parallel universes, or some principle we haven't even discovered yet, the universe might have safeguards in place to protect the timeline. Perhaps the very laws of physics make paradoxes impossible. The quest to understand time travel isn't just a sci-fi adventure. It pushes the boundaries of our knowledge about gravity, quantum mechanics, and the very fabric of the cosmos. While you probably shouldn't pack your bags for ancient Rome just yet, the physics shows us a universe far stranger and more wonderful than we can imagine. The journey to the future is happening for all of us, 1 second at a time. And who knows what discoveries tomorrow will bring. Thank you so much for joining me on this journey through space-time. If you enjoyed this video and want to explore more mind-bending science, be sure to hit that like button and subscribe to the channel. Let me know in the comments. If you could travel in time, where and when would you go? Thanks for watching, and I'll see you in the next one.